I think folks should be hearing me. Let me just check. Right. I think we're pretty much like good to get started. Can everyone hear me okay? Okay, I think this is working. All right, folks. So the plan today is like basically the majority of the work so far I've been doing in GPU mode has been really focused around like single GPU programming. And for good reason. There's a lot you can do on single GPUs, like a lot of stuff like so, if things are fast on one GPU, generally they're fast on more. Um, But I've been like particularly more interested in distributed compute and specifically like basically how to express distributed computing problems. And what I mean by this is like what are sort of the right languages and sort of like right abstraction for us to do distributed programming. I totally buy that there's like a place for people to just do like I don't know, source dot distributed parentheses their model, get it scaling. Uh, but generally like the main thing I'm interested in for today is really to talk a bit more about DTensor. Uh, and DTensor is like, let me just go here quickly. Um, so DTensor is like this abstraction in PyTorch where like you basically can have tensors that are effectively like distributed by default, as the sort of name indicates. And for the most part, like there are like no tutorials on this. Like if anything, the only thing I could find, let me just hide this quickly. I will hide this. Yeah, the only thing I could find was I think this old tutorial by Wanshao. Let me pull it up. Actually, also let me go on the voice channel on Discord if you are curious. All right. Where was it? Oh yeah. So I think it was like DTensor, GitHub. Where was the tutorial? I think it was maybe here. Yeah. Oh, this is just for the public facing stuff. Okay. So there's like really nothing here. I think maybe we should look for a distributed. Ah, there it is. Yeah. Distributed tensor.md. Okay. Oh, it does actually have a tutorial page. Let's check it out. Like DTensor, let's pull this up a bit. So it's DTensor, GitHub, tutorial, page. All right. So okay, it's alpha and it's under development, and it offers a simple and flexible starting primitives that transparently handle distributed logic. It's used in TensorParallel and FSTP2. It's an SPMV programming model. That's great. It uses a device mesh, which represents, let me zoom in a bit. It uses a device mesh, which represents the device topology and the communicators of the cluster using an n-dimensional array. And the placement describes the sharding layout of the logical tensor on the device mesh. It supports three types of placements: shard, replicate, and partial. Okay. So device mesh is basically what can communicate with what, and placement is this specific tensor that you're looking at, like how is it distributed over that like device mesh. Uh, I think the shard is self self-explanatory. This seems to be like model parallel stuff. Replicate is like data parallelism. So you might want to replicate, like for instance, your model. But like let's say you could shard your batch, which is data parallelism, or you could shard your model, which is model parallelism. Uh, replicate is what you shard over, like what, like this is sharding your, sorry, this is replicating like your model weights, and I don't know what partial is. Let's see if this is explained anywhere. Tensor is spending reduction on devices of the mesh. Okay, it doesn't make any sense to me. Okay, does anyone understand what partial means for DTensor? Let's see. Okay, all reduce and all gather. I don't get this, let me think. So starting at dimension, let's see. Okay, so the partial placement can be generated as a result of DTensor and can only be used by the DTensor from local API. Is this referring to like a partial reduction? Okay, like let's say it's a partial reduction. Does this mean like this is like some sort of synchronization group where, okay, let's really cheat and be like, what does partial mean here for DTensor exactly? What are some applications? Please give me some runnable code. Okay, hello, hello. Yeah, this is like not starting very well. I'm already like wondering what partial is with DTensor. Okay, so it describes a DTensor with each rank holds a partial or incomplete value of the global tensor that requires reduction. This typically happens as an intermediate state during discrete operations, especially in gradient computation. Okay. Yeah, if you guys want to follow what I'm seeing on screen, it's on my personal YouTube. Okay, let's go here. Partial value, partial placements, simulated, distributed. Understanding partial placement. Create a device mesh, even as one device for demonstration. Local DTensor. Oh, is partial basically like a promise that a collective will happen on this data? That seems to make sense. So is partial promise that some data of fall on it. Okay. I don't know if like Claude is just agreeing with me, but we should validate this. It's like a partial state machine. So local data, I promised to reduce this, and the promise was fulfilled. Oh, interesting. So a partial, wait, what's going on in Discord? Yeah, Mate, feel free to comment. Like I'm like really very newbie here, so like learning. Okay, so let's test this out. So okay, can I have an example to test this theory? Partial needs to become a shard. All right, partial must become replicator shard. Okay, let's try this out. Okay, just let me make sure this is actually the discrete machine. Okay, it is. This is an A100, but like with 80 gigs. So yeah, so let's do this. I code test. Basically, so it's called partial, maybe partial test, apply, and Python partial. And maybe install touch. All right, in the meantime, let's take a look at this example. All right. Oh, so we're using here like the glue backend because it's a CPU test. Create some local data. So this is just a regular PyTorch tensor. DTensor from local. I guess like from local really means presumably from local means from like within a real tensor. Like basically, we'll take a look at this API. So maybe let's. But I think there's going to be a lot of shit I don't understand. So maybe let's have open questions. Exactly. Partial is a promise. Will eventually. Okay, but this is interesting. Like, what's the use case of this API? Because presumably, if something doesn't fit locally, how would you actually call this? Because you would never be able to instantiate the local tensor. Yeah, interesting. Okay, from local. Device mask, run check, shape, stride. You're cutting off Mate, by the way. I think let's do this. I'm just gonna invite you to the StreamYard directly. I think it'll just be easier. Just give me a second, I'll invite you. It's like, all right, so let's see. So list of events which specifies the size of the tensor are different across ranks. Okay. When would I use from local? Because it assumes that I can access later. I can. Intermediate activation. So detensor to local tensor for computation. Oh, this is like a two local. I see. Interesting. Okay, two local makes sense to me because if this first of all, it's a real API. Let's double check. Two local package. Ah, it is a real API. Okay. Wonderful. So here we have So to local is a way to turn a DTensor into regular tensor. This way, regular Python machinery can work. Okay. Custom speed operations. Oh, I see. So it's helpful for sharding and resharding. Okay, I see. So, okay, also helpful for sharding. Basically, unsharding and sharding. Okay, so let's say here we want to do distributed matmul. We have two DTensors. We turn them both into local. We do a matmul. It seems wrong though. Like, wait, what is this? Okay, this example is interesting though. So maybe, yeah, full example for this guy. Okay, distributed tensor. It's yapping a lot. Let's see. Okay, I'm just gonna do this slowly. Like, let's go here. Matmul. DMM.py. All right. So in this example, first off, let's not do glue. Let's do nickel. And then I need torch run. Do I need this, by the way? Because like I still need to do. Like for torch run programs, like sorry, for DTensor programs, I still need to torch run them, or can I just assume a single notebook is driving everything? Let me think. Oh yeah, Matej, sorry about that. I just saw you in the waiting.
Hey, no worries, no worries. Check the example that I sent. It's gonna make like your debugging stuff a lot easier because you're gonna run. You can run from a single GPU or a single CPU or whatever.
But is that the fake process group thing?
Yes.
Let's see.
It's really helpful for debugging. And yes, you would need torch run. For your question, which you had like a while ago about like how would from local help you if you can't instantiate the tensor locally, it doesn't have to be like you can have, for example, imagine in FSDP you have like tensor sharded across 8 processes. I send it to multi GPU. Yeah, and so imagine you have a tensor sharded across 8 GPUs, which can be like a local tensor, right?
Mhm.
And when it's local tensor, you can on each rank call from local on it and have it as a DTensor that is like sharded on the 0th dimension, right? So that way you basically can. If it doesn't fit into memory, you can just use like as far as I know, I think the full DTensor API is compatible with meta device. So you can basically just init. That's how you usually do it. You init on the meta device and you shard, and then you load into the sharded tensors.
Sorry, then you load on. Oh, I see. Okay. Okay, so the like from local is typically just working over storage, like not actual data. You would install NumPy. Let's do this.
From local storage.
Okay, let's take a look what's going on here. So DTensor, local tensor 0, 1, 2, 3, and then where are you initializing this thing? They took a torch arrange over like 16 elements. And then you're viewing, you're reviewing it as a 4x4 matrix, sure. And then you're saying DTensor from local tensor. Okay, and then the mesh is init device mesh. And then, you're saying data parallelism and tensor parallelism.
Yes.
Okay, and then shard 0. What does this mean? Shard.
Shard is a way, like, shard means that your DTensor is going to be sharded across 0th dimension.
The 0th dimension here being the first one, like data parallelism. So data parallelism versus...
No. This interacts not with... let's do a simple example, like remove the TPU, just make it like 4-dimensional device mesh. For ranked device mesh.
Ranked device
not
mesh?
2-dimensional. Yeah, just make it a 1D device mesh.
I see. So
it's going to be way simpler. You also need to change the mesh shape, which is the second argument.
Mesh shape.
Just 4. Just have it as a 4, like a tuple of 4.
Oh, I see. Just here, like just 2 by itself?
4 now, because you will have row size as 4. So you need to... And remove the first argument. So, like, torch distributed in device mesh has 2 arguments. First one is the shape, and second one is first one is the device, which is CUDA. Second one is a list of dimensions, or like shape. And the third one is how you name the dimensions, right? Yeah, you need to have it as a tuple with or a list. This won't work because this Python downcasts it to Python downcast this to, and then you have to put a comma there. No, just put a comma after.
Oh, I see.
Yeah, it's a...
Okay, so then we see now the DTensor. Okay, and so now we're seeing this data replicated over 4 different GPUs, which is what I would expect. Yeah. Oh, it's 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7.
Yeah, so what you do is you create a local tensor on each rank, which is just an arrangement of 4 by 4. And you tell like the torch that it's this that is sharded across the first dimension or 0th dimension. That is what the argument shard 0 means. And then you tell it like to get the full DTensor, which basically says that it's gonna all gather the tensor on each rank and like concatenate it on 0th dimension. That is the next line, the dt.fullTensor. Yeah, that one also does the all gather. Like that, the above is just a print, which you can actually remove for what it's worth.
Okay. I'm sorry, trying to look at what am I looking at? So here, like, what's there is no real computation here happening. You're just like reading it. So basically, so you're doing data parallelism over all sides of 4, and
it's just an example. Like there's nothing happening really. Like this just shows you. You can see that it's basically like on each rank. Like when you create the local tensor on each rank would be a DTensor that is 0 to 16, 0 to 15. Right?
Yeah, like what's interesting to me here, it's like 0 to 15, but then I see, just here the UI looks weird from the print.
Yes.
And then okay, so let's say then this should crash then, right?
No, this shouldn't crash. I think this is gonna run, but it's gonna it's gonna concatenate it on dimension 1 because you have a 2-dimensional tensor.
Oh, I see. And what's it like? So here, this is the dimension on which you're doing your reduction. And in this case, for example, the reduction is a concatenation. So here, this has nothing to do with the mesh dim names, is my question, right?
Yeah. Okay. So the shard, or like the shard argument, is related to tensor, not the mesh dimension. Not do the mesh, right?
Ah, I see. So even shard 2 should work because then I should put the tensors behind each other.
No, I don't think it will because you don't have like the tensor isn't. Yeah, Tensor doesn't have like 3 dimensions, you know?
But then if this was, let's say, let's say this.
Yes, then this would work. Then this would work.
Oh, very cool. Okay. Okay, so then it seems to me that here, like maybe let's play around like with different, like one obvious thing to play around with would be like different reductions here. So what are the APIs available? So this is like DTensor on like, so okay, so this is so basically
you shouldn't think of this as a reduction. It's not a reduction in general. Like reduction is n to 1. This is not. This is like with shard, you're telling the torch that on each rank you have a local tensor that is a part, only a shard of a global bigger tensor, right? And with the dimension that you put in shard, you tell it like what's like how to organize it to get the global big tensor, right? It's not a reduction. Like it's not gonna be like easily.
yeah. Okay, so but then so maybe okay, so then if we want to do something interesting on D2 on like presumably like here you're gonna shard on each of these shards. Let's say you jumble up the values randomly, like to simulate some learning process, and then we want to do like an all reduce with this, right? And so we would do something like on the DTensor here. Can I do math on this DTensor? Can I say dt
Yes, you
is
can.
equal dt plus 1? Okay, what does this give me?
So if you can, yeah, it's correct.
That's correct. Okay, so it broadcasts. So okay, so even here, like this basically takes care of like broadcasting 1 into a DTensor, right? Like
yeah. So let's try another example. Like let's do dt plus this dot rank, this dot get rank, like distributed dot get rank. I don't know how you have it imported. I suppose you don't have it anyway.
okay.
Oh, I see. It actually breaks with the fake stuff.
Oh, I see.
You probably need, yeah. So everything is rank. I see. Okay. Everything is rank 0.
So we do have a real machine, by the way, just to be clear. So like we can.
Okay.
We don't have to defeat.
If you don't mind like the longer startup with nickel, then we can do that probably. That's gonna be fine. So, it's pretty simple. I can dictate it for you.
Well, I mean, just send me something to copy paste. It'll be easier.
Yeah.
Does this look fine?
Yeah, that's okay. Like the master adder and stuff is useless in general. Like just copy paste this there. That one is useless, the OS environment stuff. And
this is useless.
Yeah, that is useless, and also rank 0 and world type is useless.
Oh, okay.
And you can just do. I don't know if you need to do that, but it's init method. It's a call in init process group. There's an argument called init method. Init method. And yeah, exactly that, but without the store equals fake store, like just the end of blah blah blah, and also rank world size. You remove that. No, remove the rank as well.
Oh, I see.
This is fine. With what the init method means is that like when you do torch run, it sets rank, local rank, and world size for you, and init method env means that it's gonna take it from the environment. That's why you need to run it with torch run.
I see. I mean, I probably need a proper torch run command, right?
You can do torch run, dash dash, and proper node.
Torch run, dash dash.
And procs. dash without. Okay, let me type it directly.
And prox for node, okay.
Yeah. You should have it.
Okay.
I don't know if it's called main.py. And this is also not gonna work, or like probably gonna fail, because it's gonna do a critical error that like 2 devices. Oh, actually it works. You don't need to set that. That's actually nice.
Destroy process group was not called before.
That's fine. If you're like a good torch user, you should do like distributed or dist.destroy process group at the end, but no one cares.
Yeah. Okay, I'm a good boy.
Yeah, you usually just hang in that call for like 5 seconds, so I don't do that.
Oh, I see. Interesting. Okay. Nice.
It depends. I think my env is just broken. Yeah, now you can see it like into each of the local tensors.
Okay, so this is the original DTensor. Oh, I see. So all the prints are happening now. So now I'm seeing the prints from 4 different machines. Okay, so this is like what each of the local DTensors, sorry, each of the local tensors look like.
Yeah, those are the print DT on line 43, and then you have like the print full. You like a good thing to do is just define print 0 as like if this, like just define a function that just prints on rank 0. Yeah, I usually do that as a function because I use it a lot.
I see, something like this. Define.
Yeah.
And then it was.
And you just do with args and quarks for the dist print, and you pass them to print. Yeah, like asterisk args, asterisk. Exactly, and do that. Without the full, you have a full.
I see, true. Right. Then so now you can say this print. Full. Okay, this is more reasonable looking.
Yes.
Okay. This is interesting. So I guess let me think of it. So I like your example of just drawing one dimension at a time. Actually, what are all the possible options for mesh names? Let's see.
You can do as many as you want. Like you can just do anything. It can be 50-dimensional mesh for what
Yeah,
like you can.
I get that. I was like wondering what's the full set of strings that are acceptable.
All of them. It's depending on you. Like it's your naming. You can name the mesh name a foo for what it's worth.
Oh, I see. Okay.
Yeah, like Torch has a model that like you are responsible for everything.
Yeah. So this won't do anything.
No, it's just so when it's useful. Like in this one-dimensional example, it's not useful at all because you just have one-dimensional mesh. But for example, if you wanted to do FSDP NTP and you would have mesh of shape like 4 and 2, then you would pass into fully shard the submesh with FSDP and pass into TP the submesh with TP. Right. You can index into it as a dict.
Okay, I guess then one of my main interests with the stream at first was being able to sort of show an example of each of the different like each of the different parallelism strategies with like a minimal example to be like, okay, here's an example of data parallelism, here's an example of model parallelism, here's an example of expert parallelism with like these very, very short snippets. Do you think that's like realistic for like a 2-hour stream, by the way?
Depends. Probably like FSDP and DP and probably TP should be fine. Like if we just use torch and like explain it along the way. I'm not doing any 5-point parallelism and context parallelism for what it's worth. And yeah, it should be okay.
Okay,
which one
sweet.
do you want to start with? Like,
I think data parallelism to me feels like the most reasonable one. So maybe let's just call it data parallelism.
Yeah, so I don't think I'll eyeball this, but
I think I'm gonna try to do this without reading docs, just to sort of see if we understand the concept. So I think this device mesh here, probably all still the same. And world size of 4. So far, so good. Oh, we can just copy this whole thing, actually. Okay.
yeah.
And then the main thing we're changing is this guy. Basically, fill in the blanks here for the data parallelism.
Yeah, so one thing with the data parallelism is you don't need the tensor for it at all. Like, it's a one com anyway.
That's understood. I mean, even if it ends up being like a convoluted way of doing it. So my suspicion basically is maybe what we could do is something like you can have a class like toy model. Yeah, something like this. And then what we can do is basically input batch equals, let's say, something like this. Maybe even make it bigger, real size. Actually, world size isn't like a cool. I mean, let's say times this dot get world size for this size. All right. And then what we're doing is we're not going to be sharding the model at all. We're only going to be sharding the input batch using DTensor and then passing in each. Oh, I see. Then yeah, each rank would be, I see, okay, something like this. So basically, input batch. Oh, yeah, so this is the time to use DTensor from local, right?
Yeah, for example.
Is this right? This is not right, actually.
Yeah, this is not right. Like, I mean, it kind of like you don't actually need DTensor for data parallel for data itself, not even for the model, because you don't do any communication on data, right? You just like apply the gradients and you all reduce the gradients of the model. That's whole.
See.
So how you would do it in like raw torch is like with torch you have like the distributed sampler, etc. for data loader. So you would have like a different batch on each device by default. So you wouldn't have to do anything. But
no, but I guess what I'm suggesting is reinventing the wheel here. So
yeah,
to your point though, to your point though, like we're not actually we don't have any collectives on the. It's not like we're doing collectives across the batch, but we're doing collectives across the weights after they read the batch.
Yeah.
Oh, I see. So you would go for a pure replicate on the model, then, right?
I actually don't know how you would do this with DTensor, probably. Or like, it feels very difficult for me to do with DTensor instead of not doing it with one.
Let me see this.
Because like the only thing you do with data parallel is you just all reduce the grads at the end, right?
Correct, yes.
So I would just call this dot all reduce on the grads. Like I would just, you don't need to, like, you're just gonna go into a hassle with like your grads being DTensors and your how is that called? And your weights being tensors and so on.
It does. Oh, you use a parallelized module, which is, oh, this is different. This is not like, this is like, sure,
Yeah.
I gotta.
So this is from tensor parallelism. And I mean, it's telling you a correct thing. It's way over-engineered.
Yeah.
But yeah, like
Okay,
what this tells you.
So it's basically replicating every single layer in the model.
Yeah.
And then replicates, where is this from? Replicates from DTensor replacement types.
Yeah, I don't think it exists. I think it's just DTensor. I think it's a wrong import path, but it doesn't matter.
I see. Okay, so you get the world size, batch, create global tensor, and shard it. Global input. This looks wrong.
That is correct, but the next one is wrong. Or like this could be correct. So
broadcast the global tensor.
Yeah, you wouldn't do broadcast. You would do scatter.
Yeah.
Or all.
To convert to DTensor and shard along the batch dimension. Is this right? So global input distributed rank, that's size per rank, that's size per rank. Start along the batch dimension. I guess that is the
correct.
first dimension.
Yeah. Almost correct, because there you have like the. I mean, yeah. You should do scatter though before this. Then this would be kind of correct, I think.
So let me take this. Okay, so where was it?
I don't. Yeah, so how scatter works is you need a list of tensors. Does that work for you?
It didn't crash, but I don't think the results are correct.
Okay, so yeah, this is not gonna work, because how scatter works is like, oh, it's reduced scatter. It should be just scatter. Like, we're not reducing at all. We're just doing scatter. And now this is gonna fail. Oh, it's not actually. Are you? No, you're running the wrong file, I think.
I am, yes.
You need to do torsion. Yeah, okay. Cool.
Okay, what happened? So scatter list must be specified on source rank.
Yes, so how scatter works is it doesn't expect a tensor, but rather a list of tensors, right? And then it's gonna give one element of each of the list to each rank. So like it's gonna split the list into, you know what I mean, into like X elements. So that's first wrong thing. Like the global input is wrongly initialized, so it should be like list of total random.
But even then, like, how do you know what? Like, you need to gather them first before you scatter. So that also needs
No,
like
no. You have a empty tensor on all other ranks, where it's gonna be placed. So we can actually do this. So the line 56. Let's make it not a torch dot random, but let's make it a list of just torch dot something. Let's say I want to do rank actually. So it should be a list of tensors. So let's do torch dot tensor of shape. How do we do this? Okay, let's do torch dot once, total batch size and times 4. And multiply the tensor by this by x. No, inside the list, like we're gonna do a list comprehension.
Obviously.
Times no, this isn't right. Times like times rank, for rank in arrange get roll size. You know what I mean?
Oh, I see. This dot.
You can't call get rank because you're only on
So and rank, for rank, and
yes.
Well, that was nice.
And you need to wrap it in range.
Here, sorry.
Yes, that's correct. And you can do scatter list can be none, I guess, or like the global input can be none in the else. No, in the there. That means like you're going from rank 0 and you're scattering it to every rank, you know.
Yeah.
And this dot scatter has a annoying signature where first element is a output tensor, which is going to be, you need to create an output tensor on each rank, which is just going to be torch.empty with size, total bed size, and 4. Yeah, that is kind of correct. But you can remove the group. And you need to assign the torch empty to something, like just close it up.
Okay.
And like it's gonna be this dot scatter. What it does, it modifies the first argument in place. So you need to store it in a variable to get it out after. You know, so just take the torch.empty and assign it to a variable somewhere, and then pass the variable in. Yeah. Probably you can remove the rest of the file or just print after that, so we know it's working. Okay, something actually ran, so I think we went actually quite far, by the way. You're not printing it, I think.
So we're printing the scattered input, right?
Yeah.
Is that the right name for this variable, by the way?
It's fine. It's okay. You can do it scattered input, local input, whatever. Like, you wouldn't ever do it this way.
I see.
Okay, so the tensor is quite big, but you can see now that.
I see. Well, you taught me a trick.
Well, now it's not gonna like help you really, because you want to see that on each rank it's a different input, you know?
I see.
Which it is.
So here it's L0, L1, L2, L3. Okay, which is just the rank, I see.
Yeah.
Okay, and then 0, 1, 2, 3, which is the world size. Okay, I see. Interesting.
Yeah. So if you, okay, catch up. Stop.
Okay. So now that we can, let me think a bit. Okay, so we created this like local list of, I mean, this is interesting though, because presumably, like, again, you're creating all of these local tensors in a list when like it's totally plausible that even an individual element of this list wouldn't fit on your GPU, but you're doing like a whole list of them. And so it almost feels like it's weird to me that this scatter accepts the lists as opposed to expecting like an iterator or something. So it can just like assign a tensor to each GPU by itself.
Yeah, so scatter is just a distributed primitive that is like used in everywhere. Like this is just the signature of it. This is not DTensor specific. If you notice, we don't have a single DTensor in the input.
True.
So this
we
is
only
just
have
like
the parallelized module thing here. It's like
which actually doesn't work, by the way.
Because we didn't call it, right? Yeah.
No. It just it has a wrong. I don't remember like the static is wrong. But let's not do that right now. Let's not. It called it for you, but it's wrong. Like so you will see a warning. Yeah, up there. if you scroll up, you see warning, parallelized plan key weight could not be resolved, no submodule matching token weight. So it's a bit cryptic, but what it says is that it couldn't find a net1.weight in your state dict. And it couldn't find net1.bias in your state dict, and so on.
It's complaining about everything. It can't find shit. I see.
Yeah,
It's not working at all.
Yeah, let's ignore this for a while. Like, we'll get to the model later. Let's finish the data. So what it's telling you next is it tells you to convert to DTensor. This is entirely useless, but like for the learning purposes, we can do it. Just remove this. The next few lines that there are, like the ones that you commented, the input tensor equals. Not all of them. Just do one block at a time.
Yeah, I mean, we'll just sort of see.
Yeah.
Okay, so then this is DTensor from local. Okay, so this is doing your list trick here, which is basically it's looking at global inputs, which is a list, and it's indexing into a particular rank, which is fine because it's exactly this is world sized, and for each element index, it's going to multiply this index by batch size per rank. This is going to go out of.
Oh, I see what it. Yeah. I see what it was doing. Do you remember the broadcast that we had before? It was doing like a really dumb way.
Yeah.
What it was doing, it created a global tensor on each device, or a global tensor around rank 0. Then broadcasted this tensor to each rank. So with one broadcast. And then it just indexed into it and threw out everything else. So you can see, like, it's actually not wrong, it's just bad. You can see how our approach is better because we don't use broadcast. We use scatter, which is just a better broadcast. I mean, like, meaning.
Yeah, so this we did already, we get rid of this whole thing.
They are creating a DTensor, which was, or like the ChatGPT or Claude or whatever, was creating a DTensor, which might be correct for you. I don't mind. It doesn't matter. Let's do that for the sake. So how would you do this? Like, part of this is correct and part of this is wrong. Like, which, like, I told you that the first line is wrong, but like, how would you do the first line?
I think so. So scattered input, like now when I look at it, it's still a local tensor now, right? So this is going to be I mean, even something as dumb as this, like, would this work?
Yes, this is in. Oh, did I?
F squared along the last dimension. Oh yeah, because like it's. I think this works. Let's see. I put DTensor shape. Okay, and then I think print input DTensor. This is maybe with this print actually.
Yeah. So you can see it's correct. I'm gonna tell you a secret. This what you like. Anything you wrote there after you put in a scattered input, nothing is gonna fail, because from local doesn't do any communication at all. It doesn't invoke anything. It just, the last one, as I said, just tells Torch that I have this scattered input on this rank, and it's a DTensor that if I want to construct a full tensor, I should all gather it across 0 dimension, right? which, if you think of it, it makes sense because we did a scatter across 0th dimension.
Mm-hmm.
And like a opposite to scatter is all gather.
Yeah, so this, so presumably this is still so this is like the non-sphere prints. Let's just put the 0 here. So this is just printing the local shard that we got. So this is just printing something back. So there was no reduction or any collectives happen here. Yes. And I guess like the next step is like if we can just sum up all of these individual shards, I guess that would be like a hello data parallelism example.
Well, not entirely. You don't do anything like that with data parallelism, but yes, like if you want to reduce this, go ahead. Like it's not data parallelism because in data parallelism you reduce grads and not input.
Oh, yeah, I understand what you mean. So like basically assume, yeah, like this was your scattered grads, and then you like reduce over the scattered grads.
Yeah, we can think of it like the idea behind this, like what ChatGPT
or you wouldn't scatter though, right? Yeah, you wouldn't scatter in that case.
Yeah, but let's say like after you ran DDP, you would have scattered inputs, right?
Yeah.
That's how DDP works. And then you just need to like all reduce them. You can do that. I'll then tell you like how what's like. Yeah, this is fine. Like I think you can do it with like some DTensor magic, but I just prefer to use like distributed. It's way simpler and way more like explicit about what you're doing.
Compute mesh is none. Okay, what does this mean? Oh, no device mesh from DTensor args.
Wait, that's actually weird.
Okay, what's mesh?
So it should invoke the mesh from, or like it should read the mesh from your DTensor.
Oh, no device mesh from DTensor args for C10D, all reduced default. Okay, let me just get rid of the model shit because I think to your point, this is distracting. And then scattered put for DTensor from local. Just all reduce this print.
For what it's worth, I don't know what this error exactly means. Like, it means that it couldn't find the device mesh that the DTensor belongs to, which is kind of annoying. Or like, okay, let's actually use a different. Let's use a different approach. Go back.
Oh, interesting.
No. This is not exactly correct. This is gonna probably put it into the either partial state, or it's just gonna sum it in the rank. Like you can try this. We can try this. Like, but I forgot about one very cool API from DTensor that we can use for this, and it's gonna handle the communication for you.
Yeah, so presumably some would work just because it is like I think DTensors are tensors, and some this didn't work though.
It
didn't fail, and it gave like incorrect results.
No, it's a correct result. It's a no. It's the last one. The last one, which is a device mesh. Yeah, you see, it puts you in a partial sum.
Oh, interesting. I see. And then how do you like like exec? How do you get it to be
No,
non-partial?
I think it already executes. I don't think it's a promise because you can already see that the data is correct. Like you have 0, 1, 2, 3. To be entirely honest, I don't know the exact meaning of partial. I just know it like exists in the computer graph, and like Torch does some internal stuff with it. It's not very commonly used. Like you never do to partial yourself, or I've never seen that. I've read like most of the Torch distributed code, and I've never seen like partial really happening. So yeah. So this did a sum across 0th dimension or first dimension, I think.
Yeah, and to your point, like the data layout looks correct, but like how do you actually look at the actual data? Like why is it, for example, here when you print DTensor, it's printing actual data, but here it's not?
It's your print being broken. So can you remove the just so I see the print?
Print here?
No, just like this. Let me explain it to you. Like only the last line is your data. The last line in the print, or in the output. You have like each line starting with DTensor is one print.
Okay.
So you can see like the DTensor with zeros, that is just a print from the above, like this print input tensor.
Oh, I see.
So if you remove that, it's gonna go like it's just gonna show the well, now it's gonna show tensors above that, and then the last line is the sum DTensor. There, you see it?
All right, let me.
Okay, what is wrong?
Okay, it's like a partial sum. Okay. So I still don't quite get like how do you go from a partial sum to like an actual sum?
Well, I don't know if it invokes any communication at all. So what this did is
This is also interesting. Like it's still saying something like your local tensor is 0.
yeah, because on rank 0, your like calling sum on the local tensor would result in 0. Because the rank 0 tensor is
Oh, I
full
see. I
zeros.
see. So sum is not a collective call. It's just like the sum of the local tensor. I see. I see. Okay.
Yes.
I
Then
see.
if
I
you
see.
did how we can do like what you wanted, like reduce, actually simply, is there's a really neat API called redistribute.
Redistribute. Okay, let me see.
You can check the docs. It's very similar to how Jax compile handle stuff. It's gonna be not here. It's in Tor distributed.tensor, I think. Yeah, because it actually is. Yeah, if you do redistribute.
Okay, so we're basically doing okay, so first off, here. So we're doing input DTensor dot redistribute.
This is not the correct, go to the correct doc to it. Like this is just a, oh, right. You can see it here. Like full tensor it's actually a very good example. Full tensor, it's a syntactic sugar of the following code. Down, where you had it before. Yeah.
Oh, it perform the necessary collectives to gather the local tensors from other ranks as the device mesh and concatenate them together. So if I do, oh, I see. So for example, if I do a full tensor of input DTensor, oh,
I think
what is
it's
full tensor a method or it's like
it's a method of the object. So,
oh, I see. Okay.
You have to assign it. Like it's
yeah, so then full tensor Okay, and now if I say, let's say, this print tensor.
It's gonna fail because of that. Yes.
Okay, so this did just the cat on the dimension thing that you showed me very early on, right?
Yes.
Okay. So now we're not doing
So
a sum either. We want to do basically a sum, basically take every like 4 rows and sum them up with each other. Oh, I see. So it's kind of one of the reasons why people like DTensor is that it basically turns a lot of parallelism into you just thinking about like reshapes and reductions and views and so etc. to do
yes,
distributed parallelism. Oh, I see.
you don't need to think of like what collective to use, like how to order them and so on and so forth.
Okay.
You just
I guess as long as your like reshape foo is good, you're pretty much good. Like this is kind of
yes,
like this is yeah, I see.
it's just gonna put in correct all gathers or reduce scatter, whatever. And yeah, that's it.
All right. So then now given this okay. So given that now we have this full tensor. Oh, and similarly, when you do a dist print here, this is actually gonna synchronize the call, right? So this is like an eager execution model. So you're gonna wait for the collectives to get done, and then you're gonna call this.
Yeah, all of it is sync.
I see.
All of it is sync. I think you can do some way you can. I don't think you actually can. Like, there is a async altogether, but I don't think you can tell the this or the tensor to use async altogether.
Okay, is this correct? So let's see. And is redistribution free effectively, or no? This is
No.
slow.
Redistribution invokes calls, invokes communication. It has to, because like imagine like in our example, we have a chocolate on 0 dimension, meaning each rank has a different data, and we want all ranks to get the full like from all ranks. It's obviously gonna call all gather in the backend on the back. So redistribute is not free.
Okay. So back to the original question now. Like 2 interesting reductions we could do with this. One is like, oh, so like for example, if I take the full tensor now I could say full tensor dot sum.
Yeah, for example.
And this should give me a scalar, right?
Probably. I don't remember the semantics of sum, like if it does use a axis or not. But yeah, maybe, perhaps.
Let's see.
I think so, actually, yeah.
Yeah. This looks
I think
reasonable.
that's an easier way to do this. Let me think.
Yeah, so I guess like the question again now is like this is you like this seems fine to me as in like you pretend like the thing is distributed and then you basically sorry, like you scatter things, you then recreate like a full tensor from it, and then you can do like a reduction on it. But again, I'm still thinking of the case of like again, I want to take every 4 rows and add them to the 4 rows below it. Also, are there too many rows here? Why are there so many? Why are there not only like 12 rows?
That is a tensor from build 16, no? Or I think it's just the total batch size or whatever we did.
Total batch size, which is equals to
16,
the
yeah.
batch size per rank times. Oh, okay. So we just chose to make it this big. I see. We could have just not, I guess. Okay. Let me see. Let me ask my good boy. Manual reduce. Oh, we tried this, it crashed, right?
Yeah, there was some weird whatever thing. I think you need to do all gather, or like you can do a two-way reduction, I think, which is going to be the local sum. Like, I don't know how to do this with with DTensor, to be totally fair with you. I know how to do this with this collective myself.
Don't worry about it. This is like, I know, like I'm doing retarded stuff. I'm just like trying to see.
It's okay. Like it's a common pattern, which just I don't know. Like,
so each rank now is a full tensor, so we can do reshapes. I see. So input. So they're saying a DTensor from local. So now to get the element-wise sum across all the shards, you need to distribute to replicate, and then sum. So either you distribute over the mesh, and then replicate it to local. Each rank now is a full tensor, so we can reshape and sum. Local tensor dot reshape. World size, batch size per rank, and then reshape sum. Dimension 0. Oh. Change the code a lot, actually. No, I don't want to look at this. It's confusing me. So calling full tensor is what feels wrong to me. Like this is probably not what you want to do if you want to do like a. Or is it?
you want to do all reduce, right? We still want to do all reduce.
Yes, but like I think
Yes,
we tried this. So let's go back here, right? So if you say list dot all reduce.
you can, what you can do now is you can like again remove the input DTensor and just do input DTensor to local, right? Which is
remove the input DTensor.
No, you can just do it like convert the what I would do is like input DTensor dot to local. Like that's what I would put into all reduce.
Oh, I see. To local.
Yes. Again, like this defeats the purpose of learning about the
Yeah,
tensor.
like we're doing it back and forth. It feels like, right?
Yeah.
To...
Yeah, exactly. Like that defeats the purpose. But this is like I just wouldn't cast it into the tensor at all in this case. This is what did it miss?
I think it's not a string probably.
Yeah, you need to do Tor to distribute. Yeah.
Okay, and then this is like stateful. So basically now this will like basically now you just disprint.
I actually don't know if it's gonna like if you do in the tensor. Yeah, we'll see if that works actually. This actually might.
Yeah, this worked.
It actually does.
Okay. This feels very stupid though, because like I think this feels like we don't know how to work with DTensor, so we converted back and forth between a local and a distributed one to make this computation work.
Yeah.
So,
yeah,
but
exactly.
here we are calling an all reduce though, just to be clear. Like we're not actually like as before we were doing the full tensor and then doing a reduction on the full tensor, which would mean full tensor makes it a local tensor, and then you do some sort of local reduction on the tensor.
Yeah.
I guess it's the same, right? Like, I mean, why would
No,
one
no,
be
no.
So maybe
this is not. So, like full tensor initial, like if you have a sharded tensor and you call DTensor on it, you're gonna do an all gather. That makes sense, right?
Yes.
And all gather is kind of expensive.
That's right. Yes.
Like all reduce is a cheaper than all gather, if I remember correctly.
Yeah, I think an all reduce is a reduce scatter and then an all gather. It's like
yeah,
we can break this apart. Because they do that, I think, for like overlap optimizations and stuff. Okay, but let's look at like the whole thing we did and then just like decide if it's silly or not. So the first thing we did, it is silly. So what we did was we created locally a bunch of like smaller tensors, which in practice would probably need to be meta tensors. But we put them in a Python list, and then given this Python list, we then scatter them over all of the ranks, and so now all of the ranks have a copy of all the sort of weight tensors. Given these weight tensors, we then create a DTensor. So every rank is going to create its own DTensor, right?
Yes.
By looking at all of the scattered inputs. And then every rank is going to do an all reduce to with like a sum reduction and get us a result. Okay. So what's the silly part here? Like the silly parts feel like this is silly.
Yeah, that part is for sure silly. How it happens in reality is like you have a data loader which just sends data to correct process, right? Like the distributed sampler. I don't know exactly how that works, but like you get a badge on each rank, like correct badge on each rank.
Yeah, but presumably, I guess the reason I bring this up is it feels like design a data loader using DTensor.
Theoretically, yes. I think it's easier to just do like peer-to-peer ops. Again, like not do any redistribute stuff. So like when let me explain or what I think like when DTensor is useful is like if the communication path isn't very straightforward. Like DDP is not a good example because the communication path is insanely simple. Like you just do one or reuse in the background, right? That's why like here we're just doing a bunch of random stuff that is useless, right?
So what do you think would be the simplest example to show why this is interesting? Like would model parallelism be a better example?
Yeah, we can actually do tensor parallelism. That one is like the Torch API is insanely good, I think, for this. And yeah, it's actually very nice. I don't know if you're familiar with like how you do tensor parallelism. You do call-wise into row-wise.
Sorry, yeah. I think like this is like I remember there's like two high-level APIs.
Yeah, I remember the API. I was fixing it in Transformers whole morning. Don't worry.
For Tensor using Tensor.
Let's see if it gets it right. Actually, I think it won't because the API is kind of new. Yeah, it didn't. We have a better way of doing this.
So at least like what it's doing here is that like, let me just see if I understand why this code is wrong. It's not wrong, you said, it's just like not ideal.
I don't think, I haven't read it. I don't think it is.
We'll shard the weights matrix. Okay, yeah, so it's saying like you shard the weights across the batch dimension. Yeah, so it is doing the data loader stuff always almost, and whenever you ask it for advice here. So yeah, it shards the oh no, this is sharding the weight matrix actually, not
we're doing tensor parallelism, which is in model.
And then distribute the weight tensor across the devices. Shards here means we split across along the first dimensions. Bias is typically replicated across all devices. Okay, distribute tensor, bias, blah. Bias match. If not, this instance, DTensor. Okay, input X should be DTensor. For column parallel output features to be farted input performance distributed communication commutation use device and one portion of output. Okay. I don't think that's what this was called, right? No, this is like just here. I think, yeah, I think you're referring to the row parallel and the row linear and column linear APIs, right?
Yeah. I think we can actually recreate those. Those are very simple to create. Do you want to do that?
That sounds fun. Yeah, let's do it.
Yeah, okay. They're very simple to create, and like the author API is correct. Like first things first, like how you usually do tensor parallelism. You do column-wise into row-wise. So like when you have MLP, let me find a good blog post for this. When you have an MLP, actually, let me check. I was writing a doc for that. Let me see if I mentioned this. No, I didn't. Of course, I didn't.
God damn it, past Mate.
Yeah. Fuck that guy. Tensor parallelism. Block. Let's see. Like, there's a very good diagram that explains this very clearly, but if not, we're just gonna. Oh yeah, here it is. Here it is. Here it is. It's actually PyTorch doc. Like you can do a very nice. Advertisement for it. Yeah, I send it to.
Mm-hmm. Oh, I see them. These are the ones, right?
Maybe but the doc I sent is very nice. Like. Yeah, exactly this one. So in MLP, what we usually do is we're gonna recreate this. So, but what you usually do is you do call-wise split.
Mm-hmm.
So you shard the. I don't think it's a word. It would be call-wise parallel, I think. So what you do is you shard the matrix, the weight matrix, column-wise. Each of that gets a full input. You can see it in the diagram on the left. Like
yeah, this part here, yeah, and then yeah, sure. This is like the Megatron style stuff, right?
Yeah, exactly, exactly, yes.
Okay.
And then you can shard the B, like the second weight matrix, like the second weight matrix in MLP. You can shard it row-wise, and that way you like minimize the collectives, like minimize the communication because of some cool properties of matrix multiplication. We can actually check that afterwards. Why that works. But so what you need to do, like look at the diagram and like can you see the collectives at least a bit, like what needs to happen? X is your input, A is your MLP1 and B is your MLP2. Let's say ignore the dropout and stuff and RMS norms.
Okay, so X needs to be replicated across two machines. A needs to be sharded across two machines using column-wise parallelism. You do a local GALU, a local Y. You shard row-wise B, local computation. You get Z. And what's G here? G is the second MLP. Oh,
no, G is going to be all reduce.
So then you all reduce such that you get back a single tensor Z. Oh, like assuming no dropout, you basically all gather and you're done.
No, all gather, all reduce.
All reduce, sorry.
Yeah, because like what you can do, like if you imagine, this is gonna be a bit more difficult to explain, but like when you do the matrix multiplication, you can do it like you can split it into two smaller matrix multiplications, right? So
yeah,
like
the fine, like the linear algebra stuff is fine. Yeah, I'm just confused about the. Okay.
Yeah, and like when you split the weights row-wise, you can still do it like a local matrix multiplication, and then each rank is gonna hold like the shape is gonna be proper, but it's just gonna be like you need to sum it again. So that's the O reduce. Yeah, like I'm missing the linear algebra part, so yeah. Okay, so you kind of have like a correct understanding of this. Let's do that actually. It's very simple to call it like. Let's start with column parallel. That is going to be like really simple.
All right. So you're saying that we're going to create like a class. Maybe let's make a function for now. Let's call it colorwise.
No, class. It's going to be way easier to do it with class because we're going to require a lot of. It doesn't need to inherit from anything. We're just going to use hooks a bit to like really showcase this. So, how would you approach this?
Okay, so I guess let me just think in terms of the contract first. So this would need to take in a layer, right?
It could, yes.
And then, how can I stop this? Sorry, I don't know. Yeah, so let's see. So column-wise parallel, it's still we're like, okay, so first off, we have the like self.layer equals layer. Then we have like basically self.DTensor equals DTensor from local self.layer. And then let's say
you need to split the weight, yes.
And then are we replicating it? Let me think. So we're certainly sharding it. Like,
yes,
we're certainly sharding it.
We're sharding it column-wise. Yeah.
And then for us to say that it's column-wise means that we're doing it over the second dimension. So we're doing shard one. Right?
I think it's okay. This is going to be a bit annoying because I think weights in Torch are like transposed, you know, so it's going to be the other one. So it's going to be 0, basically.
That's fine. Okay.
Yeah, I would call it self.weight.
Okay, and then let me just get the APIs.
Yeah. We're actually not going to use them. Like, then. One thing you're missing here, like this assumes that you pass in only the shard, right? Like
this assumes you're passing in only the shard.
Like this assumes that the layer you have is already half the size. It's already sharded, you know. As I said before, like the shard 0 in from local doesn't do any communication. It just denotes that it's already sharded.
I see.
Yeah, so you would need to split the tensor here, or like do what we do and what kind of like everyone does, Torch does it, that they do it when loading. So they just load the correct shard, which we can't kind of do. So we just like you have to split it manually, right?
So basically something like you want us to literally slice the weight matrix based on the rank?
Yes, exactly.
I see.
You wouldn't do this in practice because like you do it when loading the model, right? Like you just load the correct shard.
Oh, I see. Whereas what I'm doing here is basically just like it's live resharding. I see.
Yeah.
Okay. So
yeah, like,
I mean, sure, but let's do the hacky thing because I think it's clearer. So let's say we say rank weight, right? And then rank weight is equal to self.layer.weight. I mean, what's a clever way of doing this? Actually, let me think. Let me think. So basically, I want it to go from I want basically 0 to basically I want 0 to rank 1 to have 1 over world size. Sorry, world size. Yeah, like no,
yeah,
world size.
That was correct.
Size. for the weights.
But yeah, across the 0th dimension. That's the dimension that we shard on.
Across
That's kind of
the column, yeah.
Yeah, so
let me think.
do you want to do this, or I can just tell you like this is not entirely related. This is just math.
Just give me the math. That's fine.
Yeah, so it's gonna be this dot get rank times yeah, exactly this. But that one is wrong. This dot get rank. Yeah, so this is correct. Let's just create a variable because we're gonna reuse it. So let's just create a variable that is weight shard dim or weight shard size, which is just gonna be and that one is gonna be just self.layer.weight.shape divided by this dot get road size. And remove the this dot get road size, the first one. No, that was correct. Sorry, I told you wrong. This dot get rank. Remove that one.
Oh, I see.
Yeah, so this is just tells you like how many weights belong to each rank, right?
Oh, I see what you mean. Okay.
Yeah, and then you can just slice it by multiplying the weight shard size by this dot get rank and weight dot
times self. No,
yeah, this
sorry,
is
it's gonna
correct.
be this dot get rank.
Yeah. Remove the dot CUDA.
Is this right?
Yeah, that is correct. Like you chart only across 0 dimension, so you don't like the second one. You just copy.
I see. Interesting. Okay, yeah.
You do the self.weight equals DTensor from local.
And then yeah, we have self dot rank weight, and then over shard zero. Why is it putting two shard zeros?
That's wrong. It kind of just you will also need the device mesh because like from local expects a device mesh. Don't do like in a device mesh. Just pass device mesh into the layer or into the column-wise parallel thing. You know what I mean?
Oh, I see here. Yeah, I do. So then I'll say mesh, and then self dot mesh equals mesh, and then this is self dot mesh, and then shard zero.
That
Right?
seems correct. I don't know if the order is correct. And now you also need a self.bias.
Self.bias.
Replicate what was telling you is wrong. Like think of the linear algebra. How would you do that?
Wouldn't the layout be exactly similar to like the weight here? Like instead of like, just the exact same thing, but do it over the weight? I guess the main difference would be it's a vector, and but yeah, I think this should work. So basically, if we say something like self.bias, wait, do we just replicate the bias? No, we still actually. Oh yeah, let me look at the linear algebra again.
Yeah.
So if we're doing it this way,
Look at
it's
the
still
shape
the
of
same.
y1 and y2.
Sorry, what was that?
Yeah, okay. So how it works, like, or how I think of this,
yeah,
is you need to add the bias to the result of your matmul, right?
correct. Yeah.
A result of your matmul is y0 and y2, like the bright green things. You see it? And you can divide, or like you can see by the shape what you need to do. Like, Or like even better, think of the linear algebra, right? Like you split column-wise, and then you multiply the same input with with half the big weight matrix, sharded on one dimension. Like what it's gonna do with your output? How's the output gonna look? Do you have like a scratchpad somewhere?
I do, yeah.
It's gonna be a lot easier to if you write it down, right? Like
so ax plus b, and then I have a1, 2 x b. So then I have a1. I see your point. It's the same b for both of them, so you replicate it.
wait, is it? Is it gonna be replicated? Wait, now I need to double check. I think it's gonna be sharded. I'm pretty sure it's gonna be sharded.
Yeah, it's like did you see this?
Yeah, I don't really. So let me like double check it. Like, so if you think of it in like general gem, you have mn nk, right? You can actually type it as a command. That's actually gonna be kind of helpful for you. We do mn times nk, and that is gonna result in mk, right? But what we do now, let's ignore the bias. Like what we do now is a split column-wise. So the activation is going to stay the same. So it's going to be mn. Then you do n. And you split k by 2 or by your world size. So you're going to do mn n k divided by world size in this case, right?
Nk divided by world size? You mean just a k or an n, right? Because the b is a vector.
Yeah, so, just the matrix. Like we're ignoring the bias now. You're gonna see what happens to the bias like at the end. Like so, if you do like gem on a like locally, you do mn times nk equals mk, right?
Sure.
If you do column parallel, like what we said, you split column-wise the weight matrix. So you're gonna have the shape is gonna be mn times n and k divided by world size. You see what I mean?
No. Sorry, I spaced out. Let me think a bit more.
Yeah, let me like if we start column-wise, think of what happens to the matrix multiplication when we shard column-wise. Like, how are the shapes gonna change in the matrix multiplication that I wrote down if we shard?
Sure. Okay. So we basically have so because we're doing column-wise.
Yeah, here nothing is transposed.
You basically have m over 2n.
No. First, here, let's not do any transpositions here. Like this is just activation time weight. The classic.
Activation times weight.
Yeah, so mn is your activation. What happens to your activation? Nothing. Yeah.
Yeah.
Correct?
So then okay. Oh, so okay, so it's like I see. So then if you're at the weights now, because we're sharding column-wise, then I expect n to also be the same and then k to be equals over 2.
Yeah.
Which basically means we end up with m k over 2.
Yeah, and this is gonna tell you like what the shape of bias has to be. Like what you need to do with it.
I see. Because so basically bias.
Yeah.
So.
Exactly. I hope this helped.
It does, yeah. All right. So which basically means that the self.bias. First off, you have the, I guess like we could do something similar. What you did was basically like the bias size,
Yeah.
which will be self.layer bias.shape.
Yeah.
The world size is, let's say 2, so this will work fine. And then self.bias weight equals, yeah, so self.layer.bias. And then you basically have, yeah, so self.bias size times the rank, self. This looks right.
Yes.
There's no more additional than self.bias.
You have that order. Oh, this is not working. Correct.
Equals DTensor from local bias weight self.mesh. And then are we charting over 0 or over 1? Let me think a bit. Don't tell
It's
me.
bias.
Oh, so there's only one dimension, so 0.
Yeah.
Okay.
Exactly.
Okay.
Okay. Now we kind of have the whole scaffolding actually. And we can just do the forward. So how it's usually done, how this is usually done is like you have a method called partition tensor, which is called on like when you're in it, and that basically does what we did above. Like it partitions the input, gets the correct shape, and will stuff into it. And then, like, as Torch kind of doesn't like to replace your layers, and no one likes that, it's not implemented as a layer. Like, I can actually send the implementation after. Like, let's implement it ourselves, and then we can go over the implementation and how it's done.
All right.
I have zero idea if this is correct. Like, I would just probably use like general matrix multiply and addition.
Yeah, so basically we can do torch dot optimal self.weight plus x.
Well, not this. It's gonna be x times self.weight.transpose. It's like we have to revert it to like you understand what I mean.
I think I do, yeah. So
yeah, because the weights in the linear are transposed by default, and you have to switch them up because you do x times weight transpose, I think.
Like this.
Yes, I think that's how you do it. Like that's how basically that's how it kind of does it. Okay, so there's one more thing. Okay, so let's actually assume you're getting a DTensor in this. Like your x is gonna have to be a DTensor. You can actually this would fail. This would fail because you would have mixed DTensor and tensor in matrix multiplication, which Torch doesn't support, I think.
So if x is a, well, actually, sorry, before we go over notations, x could be a DTensor or not. If it is a DTensor, that's great. Don't do anything because everything else is a DTensor.
Almost, but not entirely.
If it's not a DTensor, well, let me just continue with my incorrect thought. If it's not a DTensor, then either we need to from local the weights and the biases to make them not DTensors, or we replicate x and do a from local call on x, make it a DTensor, and then do we replicate it or do we shard it? Well, we actually replicate it.
Yeah, okay. Almost entirely correct. So
okay.
one thing, like if it's DTensor, it's not entirely like we don't do anything. We have to make sure that the DTensor is correctly sharded, or like in this case, replicated, for us to like do the matrix multiplication and be sure that it's correct, right? So someone could pass us, like the previous layer could pass us a DTensor that is sharded, right?
I see. So something like assert.
You can use a redistribute. You can use a redistribute now to like move it to your correct placement, which is exactly this.
This is kind of wild, actually, like that this works. So you basically say, okay, I don't care how this was distributed. Use the mesh that I already have and then replicate it, and then this will work.
Yes,
This feels a
exactly.
bit magical.
It's just gonna put in the correct distributed collectives and get correct places. There's no magic in that. You could write the heuristic for it yourself. It would just be very painful, so someone did it for you. Okay, also, like you redistribute, you need to return it. Like,
Why would I need to
so
return
you
this?
need to assign it. You need to assign it, sorry, so X. And also the case, like if this instance X is tensor. So how this is done, sorry, this is gonna break for you in a rather ugly way because DTensor is a subclass of tensor. And so you need to do it in a specific order. So if you basically go.
I see. So go tensor first.
You do if not is instance DTensor, because the first one is if not is instance DTensor.
Mm-hmm.
The first one, that one. Yes. Then you create a local DTensor from it. You know, like you're just gonna do from local. Yeah. In this case, if someone gave you a tensor, you're assuming that they gave you a replicated tensor. Like you can't do much stuff with it. You know, like you have zero idea on how they implemented it, if it's a sharded or replicated or whatever. So you just assume, right?
And then,
by the way, you don't need to do else. You didn't need to do any. Like you can just tab it back, like the x equals x to the redistribute. It's a no op if it's already replicated.
okay, and then you just call this. Interesting. I see.
This is almost right, or like almost entire. Like this is what you. This will work. There's also another thing, like what Tensor, like what you will see. We'll go over it later, but like good Tensor parallel layer has a thing called output layouts, or like we use that, and that basically tells you like what is gonna be the output. Like, okay, let's actually ignore that. Like in this case, it's just gonna return a tensor that is. You won't find this here. Like it's just a tensor parallel specific thing. Yeah. You can read the doc, it's actually very nice.
The DTensor, this is used to ensure that the output of the node of the user is not specified. The output tensor is sharded on the last dimension. I'm confused here. This seems to be reminding me of. So this is layout. Is this technically just you say this? Like.
Yeah, that's correct. But the output layout, what it tells you is like, imagine it as a. Are you familiar with torch hooks?
Yeah, I am, but like mostly as like ways of injecting logic before forwards.
Yeah, so yeah, exactly. Like the output layout is, imagine it as a post-forward hook, which redistributes redistributes the output to your desired placement. Like imagine you didn't want the output to be sharded. Imagine you wanted it to be all gathered.
I see. So I see. So this is like a y, and then y is equal to DTensor from local.
No DTensor from local. You can again use redistribute for this. Like there's one more argument actually, which I'm gonna tell you. This is going to be a no-op because it's already sharded on 0. But what you usually do is you have like another argument to your column-wise parallel, which is self.output way out, you know? Which you can actually assign as a replicate. Yes. Right. No, it's gonna by default, like just to the default behavior which we want with column parallel is shard 0. I think it was right.
So.
Yeah. So sorry if this confused you a bit.
On the contrary, this is one of the best explanations I've ever heard, Matei, by the way. This is amazing. This is actually very, very clear. I really like the. Okay. So this is kind of cool now. So then, like, row-wise parallel.
Can we actually like sidetrack a bit?
Yeah, sorry.
There's one more argument. Like you need to return y, but if you check like again torch docs, you see the last thing, use local output equals true. So usually like DTensor is kind of broken sometimes, and I don't know the full reasoning behind this, but like usually you just use local output as true, and then you just cast it to local tensor. Yeah, exactly. I don't know the entire reasoning for this. I would be happy to like get to know that, but yeah. Yeah, so now we should have column-wise parallel. I'm not entirely. We can actually try it. Let's try it. Okay, actually, funny. Like, let's do a. Do you know, or can you imagine how you would write tests for this? Like, how you would write a test for this? This is correct. Like, compare it to classical linear. How you would yeah, like just write a test that compares it to the same linear which you just call forward on.
So then define test.
Don't do a test, like just make it in main because you're gonna
I run it.
With PyTest, you're just gonna drop into a distributed hell.
I want to stop recommending stuff.
You can tab that one probably, except of the model. That one is useless. Like just
not keeps going.
Wow, your internal model is a bit.
Don't talk shit about internal model, bro.
I mean, it's. I can see that your GPU rich. Like my model wouldn't create that big of a linear forever.
Yeah, I think
you don't need any sequential. Just create one layer. Like we're just doing like a unit test of sorts. Don't do sequential. Just do a single layer.
Yeah.
Let's do different shapes of like input and output, just so like I always hate that because we, something that's divisible by your world size. 512 or something. Oh, and 1024 maybe. I would rather both of them. Okay. We're not going to use the parallelized module API. I'm going to talk about it a bit later.
So I guess what we're going to do now is, so basically we create the column-wise parallel. So we do column-wise parallel.
Yeah.
And as an input, this takes in the model,
you have a typo.
the mesh.
Yeah, you have a typo. It's column with 2 M's in here. That's why you don't see infinitescence.
Okay, and then this is gonna, so let's say call it model travel.
Yep.
And then assert that model. So for maybe first off, we integrate the input.
Yeah.
So x equals, say this as well. And then
do 8 more inputs. Just I don't like matching dimensions. Do like 10, 50. So, yeah, like just so we can really see what's that dimension and so on.
Then z is equal to model x.
This is gonna fail. Just print it, and we'll see. Like this is gonna fail for you. So just print it then. But I think you'll get quite you're running wrong file, I think. Again.
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 happens to the best of us. I hope I didn't file the linear algebra class here and oh right, you didn't inherit from nm.module, so forward is not working.
Cannot assign a module before module init.
Oh, you didn't call super.init.
Yeah. Okay, type error. So this looks interesting. Transpose received an invalid combination of arguments, got parentheses,
just don't do dot transpose, just do dot capital T, like the other function, without parentheses. It's just a property, I think. Or maybe I'm delusional and this doesn't exist in Torch, it exists only in checks. But I think this has exist.
I mean, I think it would have worked if we just passed 0 to transpose as well, but let's see.
Yeah.
The column-wise parallel has no attribute output layout.
Oh, you just didn't assign it. The same for use local outputs, like just do self dot. Yeah.
Redistribute argument, got unexpected argument layout.
Yeah, you can just check the doc. Probably what is the name? Like, let me check it for you actually. It's placements equals, and it has to be a list.
I see.
Short object is not a trouble. Where's that?
It's like what you suggested. Yeah, it's like this.
And yeah, that one doesn't contain. That one shouldn't be a tuple of 0 something. I think it should be just 0. Like Sharp doesn't accept a tuple. Okay, that's actually nice. Now, do we see?
If placement is partial, list object has no attribute as partial.
That's actually very weird.
Model
can you do the output layout, like remove the 0 dot? Wait.
It's like this?
It's without without comma. Yeah. I don't know if it's a very cryptic error what you're seeing, and you shouldn't for sure see this because I don't see the issue. List object has no attribute. Why would it? Oh, why wait, what is happening? Can you show me the call to
list object
right.
has no attribute special.
Oh, right, yeah, because redistribute is it doesn't expect mesh. It expects only the placements. It's just a wrong signature. That's
Oh,
fine.
interesting.
Yeah, also on line 36.
So the mesh is assumed to be global?
The mesh is there's a global mesh, but let's not go into that. The mesh, DTensor has its mesh. And unique, I think it's keywords only argument.
Placement is needed for redistribute.
Yeah, so it's keywords only. You have to
I see.
Yeah, bunch of dumb errors. If your how is it called? If your IntelliSense works, you would get those, so it's no issue.
Okay. Redistribute.
Oh, now you have it as a list of lists, which it shouldn't be. It should be someone should fix those. Someone should fix the errors to be a bit more user friendly, I think. Yeah, it's south. Okay. After fighting with Python syntax for 5 minutes, I think we should have it.
Inshallah. We'll see.
Enjoy.
Okay. I think we finally got to the area you were hinting at. They're not equal. So on at least two devices, CPU and GPU. Okay, I see. So maybe.
Yeah, so just move the model to CUDA probably. That should work. This is still gonna fail, but yeah, well.
For a more interesting reason.
Yeah, this one is oh, you need to do now. You actually need to do torso testing to assert all calls, or whatever that is. Yeah, I really hope now we have it. Okay, so we somehow failed our linear algebra class, but that's okay.
There's 75%. Okay, so they're not close to each other at all, it seems. Okay, so my best guess as to what might have been wrong linear algebra-wise is probably the stuff.
Yeah, my guess would that be as well. But one more thing, here on the, you see there's assertion error. The value of the let's actually do a bit different batch. Let's do batch size of 8. So it's going to be 8 to 1024, like the X. Or 8 to 512. Okay. Yeah. For rather obvious reasons now. I think now it's going to be wrong only on 50% or 75. Yeah, 75 actually. Oh, yeah, now you see the correct error.
Shape does not match. One is 2. Oh, interesting. So I guess the problem is in one case, oh, I see. Oh, but I thought we did 2 local.
Yeah, so we did 2 local, but what is the output? How is it, what's the, if, check up above, the m times mk. In one case, we're doing mn times mk equals mk. In the second one, we're doing the other.
You're talking about this line?
Yeah, like in the distributed case, we're doing this basically, right?
I see. So we still need to all reduce basically.
Not the, all reduce, all gather.
All gather. So basically,
yeah. So you can do this. You can do this two different ways.
Like this all gather.
No. We can do it without adapting. Like this is where the usual output layout comes in.
Mm-hmm.
You can actually pass output layout as I told you. It's a forward hook or like post forward hook, which is gonna you're gonna redistribute there, right?
Sorry.
So like your y. Okay, let's please rename the y on the line 38 to z or something, just so I can like distinguish between them, and also the returns. Yeah, so y on the line 37 is gonna be sharded across 0 dimension. That is correct. That's like the semantics. But we're testing it against a output that is full, right? So we want the output to be also full. So we can use the placements in the self.output layout to be, we can use it to redistribute, to call the all gather for us, you know?
Okay.
Yeah, so what placement would you put in to have it like all gathered? Like it's sharded and you want it all gathered. Like we talked about which placement that is.
I think what I would say is incorrect, but like my head was going back to partial because like
yeah, partial would be all reduce, I think. I don't know if it's directly mapping to all reduce, but almost correct. Like you just want to all gather, so you want like each rank to have the full tensor. So if you remember, like the full tensor is placements equals replicate.
Okay, so then it's gonna be like this.
No, do not adapt this. Like it's an argument for a reason. Like you can just adapt the test basically.
So
the column wise 54, yeah. The layout, output layout is this. Do you understand why you have a typo there, like missing bracket or brace?
Here.
Yeah. Do you understand why it's just replicate?
Do I understand? Let me think. Don't just give me a second to think.
Yeah. Oh, okay. I guess it's not a replicate. I mean, it should be. Did I miss something? I'm probably. No. You shouldn't do 2 because 2 output layout. This means, like, actually, we didn't talk about this. This means that it's replicated across first dimension and sharded across. Wait, no. This is for 2-dimensional mesh. Okay, but it's whatever. Like the shapes now match. Like, let me think why the why it doesn't. Let's see actually if we have the correct like correct numerics. So let's call all gather on it ourselves. Like we know it's all gather, right?
Like here, right?
Do it out of the modeling code just so we don't do it in test. Yes, so we do y equals. Oh wait, this dot all gather actually doesn't.
Yeah. You mean this, right?
Yeah, this dot all gather. This all gather. Let me check if. All gather. All gather works in a bit different way. Like you need a tensor list as an argument, the first argument. So that one is going to be torch.empty like y, I guess, times 4 or times world size, empty like y. I think you can't do dot, you do like list comprehension for rank in, yeah, exactly.
And just and then range, right?
Yeah.
Okay.
You have a typo in range, and also the testing is not going to work because you have a list, which should be a tensor, like torch. Oh, right. You need, again, as I said, you need to, it's not stateful in this case. You need to assign the torch empty like to a variable, which is going to be like your result, No. Like this altogether, like puts the result in the first argument, but you have 0 way to take it out of the first argument because you create it in.
Okay.
Yeah, just assign the whole list to something so you can take the whole list, the first argument.
I see what you mean. Yeah.
We did that already, I think. This is again not going to work because you're still comparing. Well, it's at least going to pass until the test.
It's still 75%. Then
yeah, but we're still testing the same thing. We're still testing y.
I see. Yeah, I see. Yeah.
No. Input list is going to be a list. Like you need to create a torch.tensor out of it. How do you actually do that? From 4 tensors, list of tensors into tensor.
Okay, so you want to make this like a list here?
No, the input list is correct. It has to be a list. But
okay.
Like then we need to convert it to a tensor. To use torch.testing assert flows,
I see. Maybe just torch.tensor.
I think you do torch.stack. You do torch.stack of input list. Yeah, but you have to do it after the list altogether. Because you fill it in altogether, you create an input list, and then you, yeah, exactly. Now, one more thing. We're calling the altogether manually just to test it, but you have output layout equals replicate.
Oh, this worked.
This is a wrong file, I think.
That's
yes.
true.
One more thing, just fix it now. As I said, we're doing the altogether manually, but we have the output layout as replicate, which I thought is gonna do it's gonna do altogether for us. So we now need to do the sharp back, just remove the output layout or put sharp 0 there, as we did before. All right. You need to call .squeeze on the input list. .squeeze 0 on line 61. Yeah. Do not really bother with this. This is just so I can double check if we did a math wrong, or we did.
It did not match. Yeah, does it seem to have?
Was wrong.
Any impact?
Wait. Oh, right. Not squeeze 0. You need to do reshape 8 minus 1. Or world size minus 1. That's whatever. No, yeah, exactly.
It's closer, but not quite.
Oh, right. It's 4 times. It's gonna be 8. Yeah, it's gonna be 8 and -1 because we have the batch size is 8. This is wrong. Like, you see, like we create a x equals like batch times whatever, and we want to reshape it back into the same shape. It's not world size. It's 8. It's just 8. Like that value is not dependent on our world size. Or yeah, that's good. This is gonna be better to just expect batch size to be like 4 or 8. Yeah, and also in the reshape, yes. Now let's see if our math is wrong or I'm dumb. I really hope this is not going to pass because. Okay, how many are wrong?
75%. But then is the shape the same? Let's see.
Yeah, the shape is the same.
Shapes are the same, yeah.
Okay, cool. So now, let me think. So either our math is wrong, or the sharpening is wrong, right? Like there are 2 places where it can be wrong. Yeah, this fails on. Yeah, just A and B exactly. This doesn't work.
Yeah, it doesn't feel like this is. I think the original one is correct. Just like this.
Yeah, that kind of feels correct.
It doesn't matter how you flip these. Like you have to get the 512s to line up.
Yeah. So let's see our shape. It's wait.
Yeah, you're not. Yeah,
wait,
we're not
wait,
gonna.
wait. Is this actually? No, I don't think we're. Our shape shouldn't be 512. It should be like 512 divided by world size. Wait, can you check up? Can you check up a bit? Wait. Huh. Or what are we actually? What's the x and y? Or like what's the weight shape that we have? 2, 4, 8. No.
8
So you
512s.
see. No, the weight shape, the model shape.
The weight shape. Yeah.
Yeah, so the weight shape is 512 by 10,000 by 1024. And you see we're also trying to multiply by 512 and 1024, which we shouldn't. We actually should do like 512 times 512 divided by world size.
512 divided by world size.
So that means like our rank weight is wrong. Like, can you print the shape of rank weight again? Yeah. That's okay. Actually, I guess since you're learning this, do you see why I think that part is wrong?
It's like, yeah, I mean, this part seems right, like 256 instead of 1024. Right? Check this out. Yeah, rank 0 has torch size 56, 512.
Oh, right. So like
1024 divided by 56. Yeah, so it's assuming the world size is 4 here.
Yeah, so that one is correct. Like the weight is sharpened across 0 dimension.
Do you think it's the problem is here with self-set weight?
I'm actually thinking like this is gonna give you the full shape, which is like the shape. So like if you print the shape of a DTensor, it's gonna print you the shape of the underlying tensor, like the local one or like the full one, you know?
I see. So I'll just print the 1024 basically.
Yeah. You see?
Yes. Like you said, yeah.
Yeah, so let's do a bit more debugging, I guess. So if we do that, we replicate. You can actually copy paste this into code and see what it if it figures out something, like why it's wrong.
So
I'm missing
just to make
something
sure.
very dumb. And what I like to do is not give it the error trace and just like you see if it figures out.
Each rank computes a portion. The way you're gathering assumes the chunks can be simply stacked, but need to be concatenated along the column dimension. Oh, I see.
Wait, do they? I don't think they do. I think this is wrong. Let's try to copy paste the code that is like what it changed.
Yeah, basically this.
Can you show the error? Like just
one second. Yeah, no. Actually, it changed the code quite a bit, it feels like, too, right?
No, it didn't. Yeah, so now like the shape is wrong because the code gave us is wrong. Oh, then we can just check the output, like what's wrong.
Your column-wise parallel shows the weight matrix along dimension 0 rows, which represent the output features, but you're setting output layout chart 0, which starts along the batch dimension. Okay.
Yeah, we're doing transpose, or did I mistake it sometime? I mean, it could be.
Were you doing something with image models or something to assume the dimension 1 thing?
No, I just remember that linear is okay. Okay,
That's correct.
Just go back like to our code, and one more, I think. Yeah. So why I meant, because like in general you do column parallel, which is shard on dimension 1, right?
Mm-hmm.
That makes sense. But in Torch, the weights are transposed, right?
Yes.
Or at least so I assume so. That's why we shard on dim 0. It's the self.weight, not the output layout. This is not gonna. Okay, let's see. Which index?
Yes.
So like I wonder what's can we do a smaller example? Let's do a model of like 8 to 16 or something like that. And batch size X is going to be 8. Yeah. And let's also print the input list and print the oh right, it's still wrong code, because there's the torch.cat. It should be torch.cat on dim 0. Bill?
Torch dot what?
Torch.cat, like gathered output, it should be on dim 0. Okay, very good. So now the shape is correct. Just print the matrices so we can just check them out. Oh, let's do this print so we just see it once. Do the gathered output actually. I think it's gonna be better. And Z. Let's do that as well. Do both of them. Maybe. What am I missing? What did I? Wait, I'm dumb. I'm so goddamn dumb. Do you remember how I told you that if someone passes you a tensor, you have to assume it's replicated?
But we are replicating it here, and
We're
X is not.
telling Torch.
Yeah.
We're telling Torch that it's replicated, but is it? We're just generating Torch.random X. Each rank has different X.
Ah, interesting. I see.
Yeah, so if you do like Torch.zeros or Torch.ones this way, it's gonna work now. I promise you that. This was the dumbest mistake I've seen.
I'm still wrong. Let's see.
What is? Hi, I'm new to DTensor. So, is it possible that weight was sharded in dim 0, but then it's transposed? The output shouldn't be sharded on. So it's gonna be like the weight is sharded. Yeah, the output layout. Let's think of it this way. Wait, let me show in the. Can I connect my YouTube to this? It might be that I'm just wrong. The correct one is, so it's this, like in general we do m n in times nk into mk.
Mm-hmm.
With torch we actually, like, the way this transposed, so we do mn times nk, that whole thing transposed. So it's going to be kn, that whole thing transposed into mk. We want to do column parallel, which is mn at nk divided by world size, world, into m k divided by world, right? But since torch is transposed, we need to do mn at k divided by world.
That's what we're doing.
I'm typing it to the chat so I can, like, double check me in the YouTube chat. The way Tensor was shaped kn before. Yeah, that's what I mean. It was sharded kn because it was transposed. No, wait, am I missing something? My linear algebra is, like, very shit. It doesn't know nuance. It's annoying. Okay, so it was shaped kn before transpose turns it into k world size n, but is it kn? But then the matrix multiplication wouldn't work if it was kn. You want to shard on, like, can you check the YouTube chat as well? Like, you want to shard on k. You want to shard on k dimension. So k dimension is 0 for us. That's why we sharded dimension 0, right?
Yeah, it should always be 0 for the. You're talking about the bias, right? So it should always be 0.
No, talking about the weight.
Weight. And shard 0 turns it into k world size. I get the shard.
0. Oh, right. I see what you mean. I'm dumb. The output layout should be sharded on the first dimension and 0.
Output layout.
So
it is outputted. It is outputted on 0.
Yeah, but it should be on 1.
I think we tried this before.
Did we? Well, we didn't try it with correct. Like, the batch was also wrong. And now we need to do a better, like, different concat. We need to do cat on dimension 1.
Yeah, the shapes are the same, but then, yeah, like now the results are incorrect again.
Let me check. Can you scroll up to the comment that I told you to write? Like, the comment with mn times nk. No, the comment.
So I just want to see, maybe we can infer something from the shape here.
Yeah, sure.
So it's the same. Okay, it changes starting here at the 4th element.
Is it 4?
Yeah, like, yeah, 0, 1, 2, like 3rd, basically. Yeah, F0 index.
Wait, 0. No, it changes in the second part. Like when you compare it to that, like first 4 elements are correct.
3 elements. Oh, 4 elements. Yeah. And then it changes here on the 4th. Which again indicates a bug in the way we're either stacking or sharding.
Yeah.
Yeah.
Which I kind of can't see though. This is so annoying to debug.
No, it's fine. It's fun.
It's not. Like this should be done in a second.
You're not having fun. Oh, actually,
What?
it's interesting. Like basically, look at this. Like even the first column here is always correct, right?
Yeah, because that's we're checking on 0th rank, and on 0th rank, like the first one is obviously correct because that one is just the.
Oh, so that's why we get 75% incorrect. It's only the 0 rank that's correct. I see. Okay. Okay, you're saying you want to look at math again?
Yeah, show me the comments. Okay, so we do mn times nk into nk. Mk, that's fine. We do mn times n and k divided by 2, which makes sense, right? Because it's column parallel, so it's sharp on the second one. Into m and k2. That makes sense. So that would be sharp 1. In torque, we do mn times n times k and that whole thing transposed.
To get km back?
Wait, can you scroll down? I think I might actually. Okay, no, it's not that. Yeah.
Wait, is one a transpose of the other?
Which one? No.
Let me just 1 second. Yeah. No, yeah, they're not transposes of each other.
There's no pattern in that.
Yeah, like I'm sorry, I'm like reading tea leaves now, but like yeah, you go ahead.
Yeah, same. Like I just can't see the. Like I already went and opened the implementation that I fucking wrote today.
You're
like,
cheating.
Or like I was fixing that in Torch in Transformers. Like it's the same thing. Holy shit. We're not adding full bias slice. What?
These hallucinations on DTensor have been insane, by the way. Like it's way better at like other stuff, yeah.
It doesn't know anything about DTensor. Let's do without bias. Let's do without bias and see what happens. Like that's gonna be first thing. You need to do bias equals false, and self-dot bias is not gonna be there. Yeah, like here comment all of the lines that contain bias. So those are like those 3.
So I do something. Okay.
And there's also bias, which you forgot to comment out. Or like in forward. And you didn't assign to self-dot bias. You forgot to assign to it.
Okay, and then here.
In the original linear. Line 62.
Line 62. Wait.
You need to do like bias equals false in the linear. And that's it. This should be fine.
Still incorrect.
Still, but let's check the outputs to see if something is happening.
Yeah, it's incorrect at the same place. Basically, starting here
it
is when
doesn't change anyway.
Sorry, it's here.
What am I missing? I'm missing something very dumb, but I can't see why. Like with debugger, this could probably work. If not, okay, so let's go over the code one more and like if that's not gonna. I really wanted to do row-wise parallel as well, like.
Yeah, I mean, granted, it doesn't seem that much harder than what you just showed me. So I think if I can get this right, I should be able to do row-wise parallelism work.
Yeah.
When you use all gather, you need to be careful on the mention around each candidate. Each rank needs to contribute its specific columns in the correct position. Here's what you need to change, just your test. Change this output layout to replicate.
We can try that. Yeah, actually, we could try that, but
where is it?
In model.
Here. Right.
It needs to be a list of replicate. Yeah, and now wait, no. Now you don't need to do the input list. Now you can just check against y, like y versus that. I would keep it there. Just. This is gonna fail because input list is not defined.
Yes.
You can just comment this out. And also the line below it, the discontinued. Yeah. I really wonder if like does the weight have to be contiguous? I mean, we would probably get an error if that wasn't there.
Transfer likes are not close.
What? Can you send me the code actually? I will test it out.
Let me send you a gift.
Yeah, sure.
I guess I'll put it in YouTube chat too, if anyone's curious.
Yeah. It's gonna be so dumb mistake, by the way. Like, I can't even imagine how dumb it's gonna be.
StreamYard. Where is StreamYard here? Let me check one thing, actually. It's like,
Let me start the drop and just test this one myself. I'm actually very curious what I do wrong. I mean, you see the logic, I just don't see what's wrong there. Oh. This is insane. It tells us that it's actually I have a for what it's worth, you can try writing row parallel while debugging this.
all right. Well, that's probably going to be also something equally wrong.
Oh, yeah, it could be.
All right, yo, Mate, I think I have some other stuff at work I need to do for a bit. I might come back online in like in the evening after dinner.
Yeah, it might be 3 a.m. for me, by the way.
Oh, I see. So never mind then.
Yeah, I'm gonna send you the fixed stuff today. Like, it's gonna get fixed. I'm not going to bed before it's fixed.
Yeah, it's like I don't like it's so interesting, right? Because like you just get the one row on the one rank working correctly. It's like I don't know what's going on. Anyway, yeah, this was the spare stream, but thank you for the 4 people who showed up, and thank you, Mate. And
No worries, no worries.
I'll see folks in a couple hours.
See you.